All right, this week we're going to talk about the last circuit in our X-ray system, the secondary circuit, and voltage ripple that comes from our circuit, how we affect that with generators, and how that will benefit our overall X-ray system. So this is the last of our circuitry talks. I'm sure a lot of you are pretty excited about that. So just a reminder that we're catching up to where we were with the primary circuit. So on the opposite side of our high voltage transformer. So we had our step-up transformer between our primary circuit and our secondary circuit, changing our voltage into kilovoltage that will eventually reach the X-ray tube. So because of that, we're actually supplying power directly to the X-ray tube, to the cathode, to the anode and the cathode. This is what is going to be responsible explicitly for that electron acceleration across from cathode to anode. So we've talked about the filament circuit that supplies the MA. So we have enough electrons actually forming at the cathode, but it doesn't actually accelerate the electrons from cathode to anode. That's what the responsibility of the secondary circuit is. So try to remember that difference, as that's a common point of confusion. Now remember when we talked about transformer law, we know that when we have high voltage, we have to have an inverse relationship with current. So current has to be low. Versus when we are in our filament circuit, we have a step-down transformer. So we have high current and low voltage. The high current will allow us to supply more electrons to the cathode. And then at the secondary circuit level, we have higher voltage in that kVp range, in the kilovoltage range, that allows us to actually accelerate those high quantity of electrons from cathode to anode. Remember that this is because when we're looking at our transformer law, we're thinking about it from the power equation side of things. So if P equals IV, I being current and V being voltage, power has to remain constant. So we have consistent power going through the X-ray system. So as voltage increases, current has to decrease and vice versa. So we've talked about this, about how we have our kilovoltage levels at the level of the secondary circuit from that step-up transformer. And throughout our secondary circuit, its primary function is rectification. So this is where we have our diodes. So we're going to convert our AC current that's coming from the wall into DC current. Remember that the transformers don't do this, the diodes do. So our diodes, which are semiconductors, are only going to allow electrons to pass in one direction, from negative to positive charges. It's going to create a potential difference across the X-ray tube, which allows the electrons to actually flow from cathode, the negative side, to anode, the positive side. So we've talked about our magnetic fields and how induction happens. So remember, at that transformer level, we still have AC current. So because it's still alternating, we have two magnetic poles that are created, a positive pole and a negative pole. And those alternating poles are actually what allow us to use the diodes. The diodes only have electron flow in one direction, from negative to positive. And this is the process that we start to convert our AC to DC. But we need that alternating current initially in order for mutual induction to happen at that step-up transformer. So you'll notice, especially if you watch the video that I'll recommend here at the end, because we get that flipping of those positive poles and negative poles, we'll be able to see the flow of electrons from both poles, even though we're just flowing from negative to positive. That'll make more sense when you see the picture, I think. Okay, great. So what we've talked about so far is the diodes and their purpose in rectification. The rectification that we see in the secondary circuit is full wave rectification, which is sort of good, but at the same time, it's still allowing for uh, the kilovoltage peak to sometimes be 0 and sometimes be at its peak level. And because we have those fluctuations, we don't have a steady stream of electrons getting to the cathode. So that's where our generators come in. We'll talk about that. So this is our step-up transformer. We're going from voltage to kilovoltage. Remember that when there's more turns in a coil, that means that voltage is going to be higher on that side. If the voltage is higher on this side, then the current must be lower on this side. We can also see the difference in voltage here from the amplitude of these sine waves. So the amplitude is higher in the kilovoltage side of the transformer, so that we know this voltage is higher than this voltage. This red guy just indicates a circuit breaker, which we'll see in every circuit just as a precautionary device. And these are demonstrating our diodes. So one of these poles will be positive, one will be negative, and then they'll flip on the inverse side of the curve, which will allow us to send electrons both in this direction through this current and this direction, but always from positive to negative. The general rule of thumb when we're looking at these diode mechanics is that we always go in the opposite way that the arrow is pointing. I kind of think of these little lines as doors. They can only go through the doors, and only from negative to positive. So if we're flowing down this direction, say this is our negative end of the pole and this is our positive end, then we can flow through this way, through this doorway, and now we're at a crossroads. We could come back this way, or we could go this way. If we go this way, remember we can only go in the opposite direction of those arrows. So there's no doorway here, so to speak. So we can't go through that way. We can only go to the cathode, flow across to the anode, and come back through this way. So always from cathode to anode, always from negative to positive. So now when we're coming back through this part of the circuit, which direction can we go? So this is still our negative side. So we can't go this way because we'd be flowing from negative to negative. But we could flow this way, going toward our positive pole, toward our circuit breaker. When that flips, say this is now our negative pole, this is now our positive pole because we're on the inverse side of that sine curve, we can follow our circuit this way and through one of those doorways. And now we're at a break in that, a fork in the road. We can't go through this way because there's, again, no doorway. We can't follow through that circuit that way. So again, we're going from cathode to anode, and on our way back, we can't go from negative to negative, so we can't go through that way, but we can go toward that positive end of the pole. So it might be a little tricky to conceptualize right now, but again, the video, I think seeing those flipping helps it to make sense. The whole purpose of this process, again, we're trying to convert AC to DC, alternating current to direct current. So this sine curve is showing alternating current because we have fluctuations both in the positive direction and in the negative direction. But using our diodes, you can see that we're only flowing from negative to positive, from cathode to anode. If there were alternating current past this point, we would see flow in the opposite direction as well, from anode to cathode, and we don't want that happening. So really, rectification is this process where these negative sides of this alternating curve are flipped. So we have just curves going in this direction. But like I said, in that case, we still see ends of those curves that are at 0 and ends that are at that kilovoltage peak. And we want that to be almost a straight line going across, so we have consistent flow of electrons from cathode to anode. So that's where our generators come in. Current is still fluctuating at this point. We need generation to smooth out that current, make that flow consistent. That amount of drop from maximum to minimum voltage from the base of that curve to the top of that curve is considered kV ripple or voltage ripple. So you might see either referring to that phenomenon. So basically this table is going from worst to best generators. We want the lowest amount of kV ripple possible because that means we have the most consistent curve. So with our single phase alternating current or generator, we still have AC happening. So this is pre-rectification essentially. And we're measuring both the bases here and at the top of the curve, but also at the top of the curve this way. So you'll notice when we have single phase 1 pulse rectified, we're only rectifying, we're basically removing those negative sides of the sine wave. And that gives us 100% because there's still peaks at 0 in our kilovoltage peak. And this is considered 200% kV ripple because we're also getting that negative side of the alternating current. Good. You'll also notice that with single phase 1 pulse rectified, there's this long pause where there's no electrons flowing from cathode to anode. We also don't want that. We want things to be as consistent as possible, which is why although we have 100% kV ripple between single phase 1 pulse rectified and single phase 2 pulse rectified, the 2 pulse rectified is better because we still have a more consistent flow of electrons from cathode to anode. With this is what we typically see with rectification. With just the diode level, we're just flipping those curves like we saw here from that negative side of the sine wave to the positive side. So we're just flipping those curves over. But we're still having points in our curve that are at 0 voltage and those that are at peak voltage. So still at 100%. With 3-phase 6 pulse rectified, notice that it looks a lot like our single phase 2 pulse rectified, but now we have a bunch of curves superimposed on one another and occurring at different times. So we're measuring still those at 0, but as we go along in our curve, you'll see that fluctuates a lot less than it had previously. We're just going from kind of those bases as we go. So they typically don't count that first 0, just the kind of peaks between each of those little valleys. So at this level, it's about 20%, and our best case scenario is high frequency inverters. This table demonstrates 4%, but you might notice in your book a similar type of curve with a similar picture where it's less than 1%. So we have even better high frequency inverters these days. So this is best case scenario. It's even more of these pulses that are superimposed on one another. So the difference between the pulses is very consistent, with nothing occurring at 0 itself. Just kind of around that peak voltage that's rather consistent. So our high frequency inverters are best case scenario. Single phase alternating is worst case scenario for consistent flow of electrons getting from cathode to anode. So as far as this week, there is a study guide posted. It's one that's already filled out, but I would recommend looking through it. Remember, next week we still have another Chapter 6 quiz. So we're currently week 6. You'll have your Chapter 6 quiz tomorrow from the previous information. And then we have another Chapter 6 quiz that will revolve around secondary circuit and generators. That'll be next week. The following week is our test for Chapters 5 and 6. So that's week 8 during midterms for your other classes. So make sure we're keeping up on that information, reviewing Chapter 5. And at the end of the day, next week, we'll also do some review. Under resources for this week, you'll notice some videos. This secondary circuit and generation is the one that's super helpful for looking at that alternation, the alternating current and how it flips that magnetic pole to allow flow of electrons from just the negative to the positive side. A couple other reminders: don't forget to submit procedure logs by end of day Friday. And if you haven't done so already, make sure that you're staying on top of that midterm evaluation for clinical ed. There's nothing that you have to submit through D2L, but you do have to make sure that your preceptor submits it through Trajexis by Tuesday, end of day at the latest.